This is the Section 8.1 Mathcast. It contains 3 lessons. In this section, students begin with a claim, and from the claims learn to craft hypotheses. And from those hypotheses, calculate p-values for one-sample tests of proportions. And finally, interpret those p-values in the context of the claim. In Lesson 8.1.1, students are given a classic narrative regarding the proportion of female managers promoted, including the null hypothesis. Then are asked to reason the alternate hypothesis. Then run physical simulations to graph and estimate the sampling distribution of men selected. Then the p-value is estimated from the graph and the result of the many simulations. You will need to be ready to provide 1 deck of cards per team, although more decks of cards can help the lesson move faster. You will also need to prepare a dot plot poster. Details for the setup can be found in the teacher notes. The lesson prompt intentionally uses sampling without replacement, so that students would be unable to find a p-value on their calculator. This facilitates the understanding and interpretation of the concept of p-value before its calculation is made relatively trivial in later lessons. The general process of all hypothesis tests is given in a math notes box following problem 8.6. This will be formalized later as the 4-step process in Lesson 8.1.3. In Lesson 8.1.2, the Trashketball narrative continues. Students see that a claim such as Elijah's can be neither the null or alternative hypothesis, and that the null hypothesis must be assumable. Then, assuming the null is true, calculate the z-score associated with p-hat, and then calculate and interpret the p-value. In problem 8.14, students realize that hypothesis tests and confidence intervals can be used to answer some of the same questions. Problem 8.15 then walks the students step by step through another proportions test. If you or your students need it for reference, there is a complete example of a one-proportion hypothesis test in the math notes box in Lesson 8.1.3. There are times when a confidence interval and a hypothesis test will not yield the same result. Since a confidence interval uses a standard error calculated entirely from samples, while a hypothesis test uses one calculated using information from the null hypothesis, they do not always match perfectly. This is discussed in a math notes box in Lesson 8.3.3. Lesson 8.1.3 takes on the tasks of deriving hypotheses from claims. This is a process that requires human judgment and an understanding of the risks associated with being wrong to determine what statements require the burden of convincing evidence. There are more core problems based on developing the student's ability to create the most appropriate hypotheses given a particular claim. However, problem 8.21 is the student's first two-tailed test and requires a conditions check, calculation, and conclusions. Remember, claims were introduced in Chapter 7. In this course, the claim is made first, and the hypotheses are crafted from the claims with attention to what outcome should require compelling evidence and what should be the default, based on the cost of potential action and the consequences of error. This claim, shown here in symbols, can be neither the null or alternate hypothesis, because the null hypothesis must be assumable. So if we were sampling ticks in the local area in order to set the standard for antibiotics use, these would be the 2 possible sets of hypotheses we could use. An analysis of potential sampling errors would show this one to be the one that we would prefer to get by default. and this error only reachable with a significant amount of sampling error. In this section, the lessons associated with sampling variability are described in general terms. Type 1 and Type 2 error terminology are introduced in Lesson 8.2.1.